Our first example is going to be to solve x squared y double prime minus 2x y prime minus 4y equal to 0. And this is 3.6.1 in your textbook if that matters to you. And so our approach is going to be that we sort of guess the general solution should look like y equal x to the m. And we're going to have to try to find m to make this work. So same as we did with constant coefficients, we take derivatives, plug it in, get an equation that we have to solve for m. So we know our derivatives from the power rule. X prime will just be m times x to the m minus 1. And y double prime will be m times m minus 1 times x to the m minus 2. That's just the power rule. Maybe like, if you'd seen x cubed, that would go 3x squared, so on and so forth. It just looks a little bit more complicated because it's to the power of this unknown m. And then when we plug this into the ODE, what we're going to find is that we want to have 0 equal to x squared y double prime minus 2xy prime minus 4y. And so that's going to give us x squared times this thing, m times m minus 1 times x to the m minus 2, minus 2x, that thing, m x to the m minus 1, minus 4x to the m. And then something that we have to recognize is that x squared times x to the m minus 2 is just going to become x to the m. That's kind of like x to the m minus 2 plus 2 is just x to the m. Same with x times x to the m minus 1 is x to the m minus 1 plus 1, x to the m. That x to the m stays the same. And so we can factor out that common x to the m. And we want that equal to 0. And if that's going to be 0 for any value x, or you can just imagine like you divide through by the x to the m, what we're going to be trying to solve is 0 equal to m times m minus 1 minus 2m minus 4. That's our auxiliary equation. And that's just m squared minus m minus 2m minus 4. So m squared minus 3m minus 4. So that's m minus 4 times m plus 1. And if we want that equal to 0, we know that the solutions are going to be m equals 4 or m equals minus 1. Unfortunately, I'm going to have to continue this example on the slide, but it's going to not take up much space. So since m equals 4 and m equals minus 1, kind of our m1 and m2, we know the general solution will be y equals c1 x to the m1 plus c2 x to the m2. So that's going to be y equals c1 x to the 4th plus c2 x to the minus 1. And at that point, we found the general solution to this differential equation right here. I wish I had something to fill up the rest of that slide. Okay, so this type of problem is hopefully really similar. The only kind of like hiccup for us is that the equation that we solve for m ends up being a little bit more complicated because of these derivatives right here. So actually, maybe I'll just write that there. Yeah, fill up that slide. Okay, so this is very similar to constant coefficients. But if you got in the habit of being able to say like, okay, I just do m to the like cubed times whatever number I saw up front times or plus m squared, so on and so forth. This one's just a little bit more complicated when you actually find those auxiliary equations. So you need to remember it's going to build that nested thing where you have like m times m minus 1 times m minus 2, so on and so forth. For the nth derivative, and then the rest of them go away as you move down the line. So for us, we just had a second order derivative, so we had that m times m minus 1 that went away. In the next video, we'll do a repeated root example, kind of start making these a little bit more complicated for us.